Today we have a seminar from Professor Antonio Lasanta from the Department of Algebra here at the University of Granada, but in the
Ceuta City,
Africa.
North of Africa city, yes, you can find.
Okay,
yeah,
and he's going to talk about thermodynamics and anomalous relaxation, Mpemba, thermalization and symmetries, and beyond.
Thank you for your short presentation, Danny. Okay, so I am Antonio Lasanta. I'm from here, from Ceuta, and also from Granada, because probably you don't know that we have a small campus here from the Granada University. We have 4 degrees, 3 of education degree, and a degree of informatic engineering, no?
Computer science?
Sí, yeah, computer science, yes. So it's a very nice city. I recommend you to visit the city. Also to try to organize some conference or something from the physics. You know, Pablo?
I know.
Okay, so.
We can also make it instead of the Granada seminar, the Ceuta seminar.
Yes, sure, the Ceuta seminar. Okay, so I'm from here, University of Granada, Nano Lab. This is Raúl, is the owner. Raúl Rique is the owner of Nano Lab. It's a very nice lab with an optical tweezer and more devices. And I also for the Spanish submatter network. Firstly, I would like to make some publicity of this activity part of the Spanish submatter network. This is the second autumn school. It's a very nice focus on phase transitions. This is the fourth lecture. You can find here Pablo. So I encourage student and postdoc, even Professor Danny, to register to this.
Is there a quantum section?
Maybe no. Are pedagogical, no researcher lectures. So I think it's very interesting. Here you can find here the website, and so I recommend you to register. Following this school, you will have a 1.5 submatter day. So a small congress in a friendly environment with a small talk for a student and young people. I think it's a very good opportunity to meet other people from this Spanish submatter network. So let's start. Mpemba and beyond. Those are the questions I have been wondering for more than 10 years. Maybe this could look old-fashioned, but it's not old-fashioned. We are always far from equilibrium, because far from equilibrium is not very good understood and studied. So the 3 questions I wonder are: can we cool or heat up faster after 1 or 2 quenches? What is faster heating or cooling, and how can we characterize the effect? The problem that we have here is that in non-equilibrium, we don't have a general theory in order to understand every problem or every system. The theory usually are system dependent. So we need to focus on a particular system that we want to study. In general, we can sketch the problem. We can go from this temperature, hot temperature, to a cold temperature, to a even more colder temperature, and from a hot temperature to a this color temperature. We can try to do this using 2 or 1 step. If you want to go to a high temperature, you can go first to a cooler one, and after that, to go to a heater one. So I will describe more in detail in the following slide. Also important is that I will not focus on mathematical details, just on physics. So I want to speak about physics, what happened, what doesn't happen, and so on. So this is the main physical question. The best well-known effect is this Mpemba effect. Anyone who knows what is Mpemba effect? Do you know? What is the Mpemba effect? In Spanish, if you want, you can try in Spanish. I don't know.
Cuando algo está a una temperatura más alta, se enfría más rápido.
Yes, more or less. If you have two cups, identical cups, at two different temperatures, you try to go to a cooler one. You can try to do something to obtain this leverage or this advantage of cool before one than the other. There are also different effects. I know you also know all this stuff, no? So this is the famous Mpemba. This is Osborne, the other professor who started to research in this effect. So for this is the so-called Mpemba effect. This is the first publication about the Mpemba effect. This is a educational publication. This is nice. You can try to do this at home, but I think will never work. But you can try to do it. So I think it's nice. Okay. But this is the classical effect. You have 2 cups or 3 cups of water, for example. You put the few cups. This one is previously boiled. You put this in the freezer or in the freezer, and you put another without boiling, another one from the bath temperature. You can find that these lines crosses. So you have here an Mpemba effect. This is a homemade experiment. You can find here in log scale. It's okay. It's like a curiosity, no? You can find this. Okay, but if you go back in time, you can find this. The old Anomalous, in the sense the Anomalous relaxation, no, that they are anomalous. Those wise men are very wise. Aristotle, Roy Bacon, Francis Bacon, René Descartes, a lot of all wise men. You can find this kind of sentence known for a long time. This effect has been even part of the popular culture in all countries. The fact that water previously warm, blah, blah, blah. This is well known, in Sweden and Russia, all that country. So it's very a curiosity, not a physical, well understood and well worked problem. So the first attempt or trial to understand this. Okay, you try to put this in a mathematical framework, and as I said before, you have no general theory of non-equilibrium. So you can describe a system, for example, using a master equation. I think all of you know what is a master equation. Okay, you can describe almost every Markovian or stochastic system using a master equation, and even in the quantum case, you can use the word, I don't know the word, Lindblad, Gonsakinski.
Lindblad, Gorini, Gonsakinski.
Yeah, another one more equation. Okay, the Lindblad equation. So it's more or less it's a quantum master equation, more or less the same. But okay, what the tricks? The first thing, the main thing or the crucial thing here that you can study this system analytically, almost, if you have a finite system, 10 spin, 10 qubits, at all, not much more. Or even if you have a large system, you can use a mean field theory or something like this. Why? Because the trick here is that if you have a probability distribution which governs the evolution in the probability space of our system, and we do a spectral decomposition, we have this, that it is the probability distribution of the system at equilibrium at the target bath. We are trying to relax from a hotter state to a cooler state. Okay, so you can write this spectral decomposition. You have this equilibrium distribution plus this term. This is the first eigenvalue, the first eigenvector, and this coefficient. Okay, it is a very naive approach or thought that you can try to find a point where this term is 0. You can cancel this term, so you only have the faster mode. This is the slowest decay mode. So if you are able to eliminate this, you can have a faster relaxation, cooling, and even you can do this heating, okay? In this case, you can see, for example, that this A2 is not monotonous and depends on the temperature. If you play with these values, you can start from a hotter point where the A2 is smaller than this, for example, that's in a cooler state, but the A2 is larger. So, in principle, this is a very strange strategy or whatever you want. Okay? In the case of the quantum case, more or less the same. You have this spectral decomposition. This is the Lindbladian. You have this. Okay, you have this is the right again matrix at equilibrium, and all this spectral decomposition, and you can try to do this. Okay, you can. In this paper, we found that we can find doing a rotation in the Fourier space where we are able to almost cancel or to do a smaller term, this term. Geometrically, what are we doing? What we do here is project, in some sense, this is the projection of the probability distribution in the direction of this eigenvector. So if you have more weight in the slowest eigenvector, your system will decay or will relax slower. Okay, I think in principle it's very easy. The problem is that we can't do this in larger system. Okay, this was done in the 1D sim model mean field, that it is almost easier. You can define a strong and a weak. And a strong Mpemba effect is when you are able to cancel this term, and when you are not able to cancel this term, only to decrease it in some range, so you will have a weak Mpemba effect, not an exponential acceleration. And you can do this also in the quantum case. So one mimic the other, in some words. Okay. And this is the first experiment in an optical tweezer that Raul knows very well. This experiment by John, that they did this experiment using trapped particles and in some sense artificial potential, not artificial because they can do it in the lab, but not a usual potential. So they were able to reproduce the Mpemba effect. You can see here the hot system, the warm, and the cold system. So I think it's a nice thing, but okay, more or less a curiosity. The next question.
On the last graph on the right, that's on the vertical axis, that's the Kuhlmann thing with divergence, right?
Yes, this is the next point. I will going to explain that in this sense, we have a clear idea of what magnitude or quantity can reproduce the Mpemba effect. For example, here is more or less a Kuhlmann labor. You can use in other cases the energy, other kind of entropy, magnetization. Depends. This is a key point because as we are far from equilibrium, it's not easy to define a general magnitude which obey an Mpemba effect. You can play with this in some sense. There are some people who say that Mpemba effect is not Mpemba effect if you don't find a crossing the temperature. It depends. But in general, we can define an Mpemba effect when we find a crossing in an arbitrary magnitude that we can define in our system, changing the system. Remember that we are always studying free relaxation. We are not driving the process. We change suddenly the thermostat or the flux of energy, so we let the system relax. Okay, it's more or less easier to reproduce. Okay, here is just question, no? What you told, the curve. Okay, we have three different systems. They are different, physically different. The key point here is that we have too much degrees of freedom. What is a granular gas? Granular gas is a dilute gas of hard sphere, which when they collide, lose part of their energy and the system cools down spontaneously. If you want to maintain some temperature, you need to put or inject some energy in your system to sustain some temperature. So here we have a temperature that we can define as the second moment of the velocity, as in equilibrium statistical mechanics. What fixes the temperature is a thermostat that we vibrate or put at each particle some kind of stochastic thermostat and sustain the loss of energy. Okay, the losing of energy. This is a water model, even more complex because we have more degrees of freedom, and the MOX complex maybe is a spin glass near the spin glass phase because you have an infinite number of minima. It's very difficult to reproduce this. So here, this is particularly well illustrated because we have analytical a prediction of the behavior of the granular gas. We have a temperature, okay? This equation describes the evolution of the temperature depending on the energy that you inject in your system. So, but what the trick here that we have the evolution of the temperature, the second moment of the velocity of the particles, but we also here this is enlivened to another equation. This equation is related to the A2. The A2 is the first moment of the velocity. The first moment of the velocity. That is the kurtosis. So, again, a naive idea is try to fix a very rare kurtosis at the beginning, and so you will have a different relaxation because this equation that reproduces the relaxation is a slave to this. So if you start on a very particular initial condition, you can see the Mpemba effect.
And what is that, the A2?
The kurtosis.
You have these two equations, they should be related.
Yes.
But in the first equation, there is no A2. Is it inside this new?
Which one?
In the previous one?
This.
There is no A2.
Yes, this is A2 is here and here. Yes. Yes, and here you can find this, and the T is in this also in this equation that you can put here. Okay. The problem is that in kinetics theory, people rescale every variable and looks like I don't know, I'm a bit messy.
You assume Maxwellian distribution?
No. This is the point that granular gases are intrinsically out of equilibrium. You never have a Maxwellian
You still
distribution.
define temperature as the second moment of
Yes, I don't fix the distribution. Just at the beginning, I fix a distribution with these tiles, with the force moment. And let's evolve freely, and I will measure wherever. Yes, the kurtosis. I use in the simulation, we use a lambda distribution with this extremely rare kurtosis. Are physical, but extremely rare.
Okay, so basically here the temperature is the second moment of the velocity.
And this is the first moment. What I mean is that you can't describe the system, the evolution of the system, the distribution probability, just using the second moment, as in the Maxwellian case. You need another degrees of freedom, the first moment. So you can describe that your distributions are not Maxwellian. You have strain tails. So water model. Here we use, I also say another trick, not our trick, that here we have more or less like 2 degrees of freedom, the kurtosis and the temperature, no? That's more or less. And here in water model, we played with non-equipartition because in general in water model you have potential energy between molecules and kinetic energy. Okay, in general, in a certain equilibrium, obeys the equipartition theorem, and you have and a half of the degrees of freedom at a half of the energy at each degrees of freedom. But what's happened if we put all the energy in the rotational, for example, degrees of freedom or potential energy or degrees of freedom, and smaller and smaller energy in the kinetic modes. So intuitively, you can think that particle interacts through collision or through the kinetics energy. So if you put less energy, your system will cool slower than if you put all the energy in the kinetic mode. So this is the game that we use. And even more, we did this putting all the energy in the vibrational, almost quantum degrees of freedom. So you can find that your system is at equilibrium, and this is putting all the energy in the vibrational degrees of freedom. You can see that the relaxation is more slower than the other one. But the problem here that this is picosecond, is not measurable. It's impossible to measure this. Okay, so this also answers your question about which magnitude or what magnitude can you use to do this. And the last one in this approach is the spin glasses. The spin glasses have inside another degrees of freedom, which is the coherence length, the correlation inside the spin glass. So we were able to age the system and internally change the coherence length, but not the energy. So we were able to reproduce with the energy an Mpemba effect. And playing with this trick of age our system. When you age, I didn't put the plot, there are more plots, but in general, what's happening, you have, when you age your system, you put your system in a temperature, and let's evolve, the system and the spin glass is not in equilibrium, so some degrees, internal degrees of freedom continue increasing, so the velocity of the relaxation when you change your thermostat is different than when you put your system in a particular state. So another trick to reproduce the Mpemba effect in a very different system compared with the previous one, which is more, I don't know, it's more clear, no, more clean, no, cleaner than this case, but it's okay. It's an Mpemba effect. Okay, another question. So we have seen that we can have an Mpemba effect, okay, but another naive question, maybe if I'm at this temperature and I want to go to this temperature, I can try first to put my thermostat here, go faster, no? Because you have this relaxation, and when we are just at this point, change the thermostat, so I naively can expect that my system stay here. Okay? In equilibrium, you consider classical thermodynamic, your system is described by temperature, volume, pressure, chemical potential, and whatever equilibrium. But what you find is that your system have this jump. So the Kovac effects prevent you to take an advantage of doing this kind of trick. This is the Kovac. Why? In granular gases also is related with the kurtosis. The kurtosis, where we found before here, this relax on a different time scale than temperature. So when you study the evolution of these two magnitudes, where you find that while the temperature is at this point, the kurtosis doesn't correspond to the kurtosis that your system should be at this point. So this jump is produced by a jump in the kurtosis, by the relaxation of the kurtosis. In other words, you have a competition of time scales of your system. This is what's happening with this. In an experiment, this is together with Professor Rica. Okay, it's something between what we did and what I explained in water and granular. When you have an overdamped and underdamped particle, you have kinetic degrees of freedom, kinetic energy, plus a potential degrees of freedom. Okay, and you have two different time relaxation. And if we try naively to go from this temperature to this temperature, using this relaxation curve, and just at this point, we change suddenly again the thermostat, we see that our system behaves in this way with the jump. And this is because what we are measuring that here, that is the potential energy, because the kinetic energy is not possible to be measured in experiment, Raúl? Era verdad, ¿no? La energía cinética, the kinetic energy, we can't measure the kinetic energy at any point. We can.
Water, no. In this experiment, we measure something.
But what is happening here is that the part of we have two time scales, and this 2 time scale produce this jump, because we are here only measuring the potential energy. We have 2 time scale, one related with the kinetic energy, and the other one with this. So for this reason, we see this. You can find here what we did with the thermostat. We put this to the cooler temperature, and at this point, just here, we change this and maintain the temperature, and we see the Kovac effect. So the Kovac effect is also present in this kind of simple system. This is described just by a underdamped Langevin equation. Okay, so is also nice. Another different strategy. If we try to do something that is well known in the people who works in alloys, no, metallurgy, alloys, and things like that. Yeah, you have pre-cool or preheat your system before go to a final temperature. Okay, and this is what these people did. They want to go to here, and instead to go directly changing this temperature, they try to go to here, and at this point change the thermostat, and they went to this point. And what they found was just this, that we have here that doing this process that in principle looks more complex or slower, you can find that the relaxation time is much faster than this one. That is the normal relaxation or the natural relaxation. Okay?
Why is the M start? The M on the horizontal axis?
The magnetization, and this is I don't know, this is the staggered magnetization, this is the magnetization. This is a 2D easy model, but with using amine field. And something related with this is that we... Me ha quedado sin pila. Okay, me pongo aquí. What we did is age our system in the same spirit that this, and we were able to change the coherence length inside a 2D spin glass, and we spin glass AC model, and we are able to reach this region faster than if we do the normal relaxation. Is in the same spirit than in the other case. Okay, there are different anomalous in the sense that it's not a normal relaxation. And Raúl, can you explain this? And the third question is, far from equilibrium, heating and cooling are equal or are equivalent? No. Not always, but in general, no. Okay, you know also this problem. You can also explain this. Okay. This is a very nice experiment that we did with Raúl and Miguel. Miguel is not here. Here in the Raúl's lab. And in this case, we also use, again, the Kuhlmann-Leibler entropy, which is a magnitude that compared to probability distribution. This is a number magnitude with a scalar. You can say if your probability distribution are equal or different, and you can define a Kuhlmann-Leibler entropy depending on time. So you can monitorize the evolution of your system doing this. And what we found here, that if we define 3 temperatures, cooler, hotter, and 1 temperature, and we define using as a measure this Kuhlmann-Leibler entropy, and we put 2 points just at the same distance, equidistant, and we. Okay, thank you. And we change the thermostat to a 1 temperature. We find that heating is faster than cooling. Okay, that's what you can find here. Heating is this, and this is cooling. So you find this is a very, very simple and nice experiment. You have a particle trap with a laser in water. And you can measure the probability distribution and all that stuff. You can find this. Okay, this in another case that you are going from a hot temperature to a warm, and you also do this experiment going from a colder temperature to a warm one. Okay, the main criticism about this is that you are doing all this using this measure. So is this natural or is artificial? It's a question that you can ask or you can wonder about it. So the natural answer, at least for us, is let's try to do a simpler experiment that is going from a hot temperature to a colder one, and from a colder one to a hotter one. It's the simplest experiment that you can do. But the problem that we can hear that we can't compare between two probability distribution. You need another magnitude that doesn't depend on two probability distribution function. And this is the Fisher information. Fisher information depends only on one distribution function. And you can also define a world framework called thermodynamics, because you can define also a velocity in the probability distribution space and so on. And effectively, you can find that heating is faster than cooling in a very naive experiment. So in general, in this kind of problem where you have an harmonic potential over damped Langevin description, you can find this. So it's very nice that we found this. Okay, but is this also true? Not. It's partially true that it's easier to find an asymmetry between cooling and heating, or heating and cooling, depending on the system, on the parameters of your system. For example, in this 3-level system, you have a thermal bus, you have a difference between energy levels. So you can play with these values, and you can find heating faster than cooling and cooling faster than heating. So it's not universal, but for equilibrium, you can find this kind of anomalies of relaxation. Okay. What here the point? Just this, no? You have again the same spectral decomposition. You have this coefficient that depend from the initial temperature and to the bath temperature, and this coefficient depends on the bath temperature, the eigenvalue. Okay, so if you can play with these values, you can find one kind of relaxation or another kind of asymmetry. Okay, this is always the key point are these coefficients. If you think of this term from the lens of geometry, you know, you can put your mind in your probability space and look into the direction of the eigenvalues and the eigenvector, and you have a more intuitive picture of the behavior. So it's not so rare or so anomalous to have this kind of effect in non-equilibrium system. And Danny, can you explain?
The same problem.
The same but quantum, okay. we didn't think too much about new ideas. we did the same, but in quantum. The key point is to try to translate the measure that we did in classical system in quantum system. Instead of curva label, we use the fidelity or Newman entropy, whatever you want. Instead of classical feature information, you have the quantum feature information, and so on. So it's not surprisingly that we found just the same. We have here the projection of the first mode in the first decade mode, and the direction of the first slowest mode, and we compute analytically almost, in this case, in one thermal qubits, the same thing that before. We also explain this in a harmonic oscillator, and if we plot here the projection of the eigenvalue of the Liberian operator, we can find here, this is very interesting, that we have a lot of number of fast decay mode. Meanwhile, in the cooling process, we have almost a slow decay mode. And we see at the projection in the area of the decay mode in heating and cooling, we find that cooling are larger than the heating one that are going to the left. This the same mechanism or idea. Okay, this is also the quantum Brownian motion that is also well defined, and we found just the same, that heating is faster than cooling. It's an extension to the quantum case. It's also interesting. And now my last research about this kind of phenomena are these. Let's try to see to the problem through a different lens. World is observable when the number of a state is large enough. In other words, if as if we were working before with the Schrödinger picture, we change to the Heisenberg picture, which is observable, and we compute the eigenvector, eigenvalue from the right of the master equation. Okay, and under Santa's third time consideration, you can find something like in the previous case, but the nice idea here is that we can reproduce with this picture the three effects that I told before, that I explained before. You just need that the slowest observable be non-monotonous. I will show in the next slide more or less a sketch. So we have, instead of the probability distribution description, an observable description, more or less the same. So this is what we found. if you consider this observable, which is not monotonous, okay? This is the staggered magnetization because we are considering 1D Ising model, okay? We fix 3 temperature points. We can go from D, from D, from D, from here. We can do this kind of process. We can, depending on the target point, we can reproduce one or another effect, depending if we are going from the left to the right or from the right to the left. Okay, we reproduce the preheating effect that we saw before. We can reproduce, this is the Mpemba effect. We also found the inverse Mpemba effect, which is heating instead of cooling. The preheating effect, we can find also this. And the asymmetry, depend if we are going from here to here, from here to here. We can find an asymmetry heating, cooling. Heating is faster than cooling, or the reverse effect. So we can, this is a general, in some sense, more general process or description. We did this also, this is in a 1D Ising model with magnetic fields, and recently we have sent to publication this, which is in a 2D Ising model with, I remember, it's large, near the thermodynamic limit, I don't know, 1000 or something like this spin. So this picture working with the observables is a very, very interesting approach, because one of the main questions that we did, me and all the scientific community, about the Mpemba preheating and all the stuff, is about the infinite or thermodynamic limit, because we couldn't explain well how to reproduce this in this kind of system. So thank you for your attention, and remember, this is for Raul. Actually experimental, but the fun is real. It's a list of publications. If you want to discuss some technical points, some mathematical points. Questions? Danny.
How common is this effect? You really have to like play around with parameters to get. How common is this effect? Like, is it some very particular parameters, or is it?
How common?
Yes.
I don't know. How common in our computer? Very common. In the nature. Okay. You are theoretical. Yes. Okay. So you will understand me that. For us, we try to simplify every problem. So the first attempt I did is try to reproduce the Mpemba effect, for example, in a gas of balls. So, because in general, in experiment, in nature, I think it's not so common, at least, measure or reproduce this kind of effect. Because if you try to do the original experiment of using water in a freezer, it's not very, very easy to reproduce. But far from equilibrium, at least we have demonstrated that you can find this kind of effect. Can be at some point, at a certain point, natural. Because far from equilibrium, we have no very good intuition about what's happened. So, but if you ask me if I can do this at home, no. Me no. Maybe Raul can do this, some kind of this. In your lab, yes, more or less. Yes, but, yeah, the Kovac, yes.
Mpemba, no, asymmetry, yes.
Asymmetry, yes.
Okay, two.
Raul 2, Antonio 0.
And how did Aristotle knew about this? If he didn't have a freezer, he didn't live in. He lived in hot countries, or how did he?
Yes, people from cold countries said that if you want.
But Aristotle didn't live in a cold country. He was Greek.
That's very smart.
Or he heard from someone, he didn't have a freezer.
You say in.
The quote
Aristotle, I don't know. He wrote this in a meteorological translation or philosophical translation. He said that if you are in I don't know, sleeping in the forest, and you try to freeze water, you before put it to boil, and after that put there and will freeze before. I don't know.
I mean, I think that even in Greece they have mountains where winter is very
Water. No, also the water.
I mean, maybe someone there are we identify all these countries with Mediterranean, hot and warm.
Also, water was purer than now, no? More pure than now. Now we have microplastic, no? All that stuff. So.
I have a question. During the relaxations, have you, regardless of what quantity you are observing, whether it be magnetization or anything else, have you tracked down what happens with a divergence, like the Kullback-Wheeler divergence? Do you have the same graph of delta D or something like that? I mean, in the classical case, in the quantum case, maybe the fidelity. But do you have the same graph that left on left or?
What do you mean about this?
Those graphs, like those graphs
Yes.
of the Kullback-Leibler divergence.
Yes, if I write here put here the Kullback-Leibler divergence, I think you have a non-monotonous shape. Yes, yes. For this come to my mind from this, thinking about the monotonicity of the Kullback-Leibler. I thought if we have another potential that we can measure, because here we can measure or write a Kullback-Leibler divergence, because no, we can't, because we have a large system, and you can write a probability distribution for a large number of spins. So we need to use this other point of view, descent, because we can more than 5 or even 10 spin, you can't write the probability distribution function. What's the probability that your spin stay in a point? It's impossible.
You can't even track it because you don't have.
For this reason, in these experiments, we could measure this kind, because we have an histogram. The position of the particle is very easier to measure in the lab.
Because the Kullback-Leibler you make between the probability distribution of your system at this time with the target.
The target, yes, with the target, yes. This is just comparing this and this.
We have made all the thermalization process
Yes.
in quantum, and we see with the fidelity,
Yes.
we see this kind of people. You want to thermalize, and instead of going monotonous to this temperature, you go up. And
Yeah, sure. I forgot that another experiment that we did is to do just the reverse experiment. We did first this, going from the hotter to the warmer, from the cooler to the warmer, and we did the opposite, going from the warmer to the cooler, to the heater and to the cooler. And we've also found that heating, going from here to here, is faster. It's the symmetry also in the reverse process.
Okay. More questions? Well, thanks, Antonio.